Namaskar. I am Professor Pavitra Nath from the Department of Physics. First of all, I am thankful to the organizing committee for inviting me to this talk, to this event as a resource person. Honorable Patron Mr. Midul Yadavji, Chairperson Madam Dr. Jayashree Chakraborty, members of the organizing committee, and my dear student friend. I am told that for today's event, the target audience are the undergraduate and higher secondary level students. So therefore, I have designed the content of my talk according to the target audience. So from the next slide onwards, you will not see my video clip. Rather, I will put my audio clip only, since the file size will increase if I put the video clip in my presentations. So before I go into my topic, let me give you a little glimpse about my university. So this is the bird eye view of our Tezpur University. It's a beautiful lush green campus spanning over an area of around 256 acres of land. Around 4,000 students are currently studying in different areas in science, technology, engineering, humanities, and law and management. We have around 300 plus faculty members, and last year the university has been accredited with A plus by NAC. So as you are aware that in many places in Assam and northeastern region as a whole, people consume the groundwater as their primary source of drinking water without bothering about the contaminations due to different inorganic and organic substances. And as a result of this, you encounter different diseases. For instance, the here one that if the groundwater is having excess amount of fluoride, then the person may encounter different diseases such as dental fluorosis and skeletal fluorosis. These are some of the diseases that you can we often see in our region. Again, during rainy season, in many places, especially in rural and remote areas, our groundwaters are often contaminated with different microbial particles, especially the pathogens and other micron-sized slits particle. So, as a result of this, now people consuming the groundwater as their primary source of drinking water. So, they are often encountered with different diseases such as diarrhea, gastroenteritis, something like that. So analyze the groundwater or the contaminations, level of contaminations, what we require some instrument which I have shown here. This is a nephrometer to measure the amount of microbial particle present in it, and one such the pathogen that is present in the in those water resources. So again, after the rainy season is over, we often hear the news of malaria that is occurring annually in our places. So this is the pictorial representation where malaria occurs throughout in our country, and where Assam the prevalence is very high. So but the person living in the rural and remote areas, they don't care about the diseases at the initial stage, but later on when the fever level goes high, then only he or she visits the distant places. But by that time, it is too late for him to get a proper medication or to get recover from the disease. As a result, we hear lot of lethal or fatal cases every year. So these are some of the burning issues that I'm trying to address through our work, and to through our work at Tezpur University. So the issues that I have mentioned in my earlier slide, it still exists, and which is the reality of our society. And the reason why we are unable to overcome these issues is due to lack of resources or the clinical laboratories, or you can say the analytical instruments available in remote and rural areas. So to address these burning issues, we at Tezpur University are trying to develop an alternative platform that can be used at a personalized level, or you can say as a point of care level. So we try to address this on a smartphone. So before I go into our work, so let us have a look on the evolution of the mobile phone technology. The first mobile phone came into existence in 1973 when Martin Cooper, the then CEO of Motorola company, he first demonstrated the functionality of a mobile phone device. So since then, the technology has evolved like no other technology in the mankind. Today, approximately 7.5 billion broadband subscribers are there across the globe, and this technology is evolving at a tremendous pace. So the penetration, if you look into this histogram, actually how the technology, how this mobile broadband subscription is there, worldwide it is like growing at the rate of 25% or more than 25%, whereas in the case of least developed countries it is growing at around 55%. It shows that irrespective of the location or the geographical conditions, the smartphone technology has reached to the far remotest place in the world. So you can say that it is the most evolved and most penetrated technology in the mankind so far. So today, by smartphone, what we know basically, apart from being used for communication purpose, it is embedded with lot of features, such as it is embedded with a lot of sensors, particularly accelerometer, gyroscope. As you all know that a rear camera and the front camera is there, magnetometer and a barometer speaker. It has a Wi-Fi features and Bluetooth, GPS. That means a smartphone is not only used for communication purpose but also can be used for a lot of other work actually which we do in our day-to-day life, and therefore it is one of the most user-friendly tool that we all actually carry nowadays in our hand or in our pocket. So apart from these, the smartphones are actually it comes with a lot of user-friendly interface such as Android operating system, then Microsoft, then iOS for Apple iPhone, and RIM. So these are very very user-friendly, as I would say. So using again the optical components that are available in the market, in the small optical components, one can integrate it with the smartphone, and you convert the phone into a very useful sensing device or imaging device rather. So the combination of both optical components with the smartphone and applications, you can really convert your phone into a very very user friendly, handy and low cost sensing device that can perform as same as your laboratory gauge sensor or an imaging system. So I would like to mention here one such important sensor, which is called ambient light sensor. It is actually embedded in the front panel of the smartphone. It has two photodiodes. I have shown here the characteristic of the photodiode, and which is sensitive from 350, or you can say the 400 approximately, all the way up to 950 nanometers. And the IR LED is there is another one LED is called the infrared LED, just close to the this photodiode. The use of this ALS sensor is to optimize the power consumption by the phone itself. As you know, when a phone when you receive a phone call and you bring your phone near to your ear, the screen automatically goes off. It means that the IR LED, when the phone goes on, that means you bring your phone to your skin or to your ear, so the IR LED will go on and it will reflect the signal from the skin, and it will be detected by your photodiode, and thereby the photodiode will send the signal that the phone will go off, the screen will go off rather. So that way it will optimize the power consumptions. So this is the actually the work of this embedded panel, ALS sensor panel of the phone. So this detector is very very sensitive, as I mentioned, from 350 to 950 nanometer, and this can be used as a detector for development of different sensors on on a smartphone. Again, to convert the data into a readable format by your sensor, so what you need is an applications. So basically, suppose you want to measure the fluoride level in water. So we measure the fluoride level in terms of either micromolar or milligram per liter, right? So for that, the detector reading will be in the form of either, it will either measure the intensity or the change in the wavelength. But in order to convert that intensity into that micro millimolar or micromolar scale, you require an applications. This can be done, or these applications can be developed on a certain platform. This is one such platform is called the MIT App Inventor. So this is just a pictorial representations that one such applications we developed for our work. So MIT App Inventor is basically a number of blocks that you have to assemble in a certain order to obtain your applications, and this application will convert your sensing data into that format, whether it is in a milligram per ml, or it is in the concentration, or whatever you want. These are the some of the blocks that can be assembled using this MIT Inventor platform in a certain period, or in a certain in a certain fashion, or in a certain order to develop the application. It is very user friendly. Those who have basic skill on C programming or other programming language, they can easily do it at home. So by using different hardware and software components, and also of course with the optical components, we can convert you can convert your smartphone into a very useful, user friendly and handheld sensing or imaging system. And this sensors or imaging tool is basically a standalone. It means that no external power source is required, because the smartphone battery can be used to powering the device. Similarly, LED flash of the smartphone can be used as an optical source. Therefore, you can call this is a completely standalone system. And now in our work at Tezpur University, using this standalone or smartphone device or Samsung device, we have detected fluoride, iron, phosphate level within the phone itself, on the phone itself. So let me give you one example how we have measured the fluoride level in water. For this, we follow the standard protocol that generally the scientists or the laboratories usually follow in their lab to detect the fluoride level in water. Here we use this APHA method 4500. Here in this technique, a particular reagent called acid zirconyl spadness colored complex. This is a standard reagent. We allow it to treat or react with the fluoride contained water, and with the increase in concentration of fluoride level, the color of this reagent gradually bleaches by fluoride presence in the medium. So this can be actually recorded, or this can be detected only with a spectrophotometer. And this is the characteristic graph of the spectrophotometer. You can see where the intensity of the spectrometric data at 570 or 568, it is varying, when the concentration of the fluoride is changing one by one. This is the actually this shows the steps how we have what one has to follow to obtain this reagent. So this picture, the left hand picture shows the schematic representation of the work. So here the flash LED of the smartphone is used as an optical source. It is coupled with an optical filter at 568 nanometer, where our sensing data is shown different reading. So 568 nanometer will allow only 568 nanometer of light to pass through this optical fiber, and then it is coupled with this cranial, or you can call this as a optical setup. So the light signal will pass through this setup, where the sample, your fluoride sample, is kept in a cuvette, and as it will react, or you can say that the signal will get absorbed depending on the amount of fluoride present in the sample, and that way the modulated signal is received by the ALS of the phone. And this is the prototype that we have developed in the lab. So this slide shows the sensor response for different concentration of fluoride present in water. We start from 0 all the way up to 2.2, approximately 2.1 milligram per liter of fluoride in the sample, and we found that our sensor is behaving almost linearly with the increasing concentration of fluoride in the sample. So this linear response is very important as far as the design of a specific sensor is concerned. So this, by using this, we then perform the our sensor performance on different smartphone, and we found that similar linearity response has been observed. Of course, this tool, the sensor performance, the slope of the response is different in two different smartphone, which is obvious uh, because the specification of the sensor or their hardware design of the sensor may be different, but that is not an important thing. But the important thing here is that how linearly the sensor is behaving with increasing or decreasing concentration of fluoride in the medium. So this is what we have demonstrated in our work. So after having the linearity in the sensor response, we measure the water qualities or water fluoride level in water from different field collected water sample, and we validate our data with a standard spectrophotometer that is usually used in the laboratory. So these are the data. I mean the this is the data for blue blue pillar shows spectrometer data, and the red shows the smartphone data. In all cases of water sample which we have collected from different places of Assam, we found that the spectrometer data and our smartphone fluoride sensor data are almost matching. This indicate that the smartphone sensor which we have designed in our lab can be reliably used for detection of fluoride in water. So this is a pictorial representation of the applications that we have developed for detection of fluoride in the lab. So this is the applications which you have. It's called the AppSense applications. So this application will allow it to calibrate the sensor within the phone itself, and it has a feature to record the data for of unknown water samples, and it will guide you to what are the steps to be followed to measure to measure the fluoride in water. So if the fluoride level is exceedingly high, or it is exceedingly more than the permissible limit, then it will indicate in the red, the cross indicate, and it will alert the user. And if it is suppose below the permissible limit or it is safe, then there will be a tick mark with a green tick mark on it. The application also has a feature of storing the data within the phone itself, or you can share the data within a distance laboratory, or you can also transmit the signal or data which you have recorded on a smartphone to a distance user, or to a person that is located in distant places from the from your place. So these are all this is the applications that we have developed in an MIT inventor by one of our PhD student. As I mentioned in one of my earlier slide, that during rainy season our groundwater resources are contaminated with different microbial particles, including pathogens. So that becomes the water medium or water turbid. So it means that how many number of particles or microbial particles are present per unit volume in the water medium. So to estimate that number, what we do is we use the light scattering principle. Here the light signal is allowed to pass through a parallel beam is allowed to pass through the medium, and this particle, because of the presence of this microbial particle or micron sized particle, it will scatter the light in all possible directions. If the detector is placed just in the forward directions and it measures the scattered light signal in the in this direction, we call this as forward light scattering. But when we measure in other angles, or in right angle triangles, or at right angle triangles to the incoming light directions, then we call this as a scattered light signal intensity. Now, when I record the signal intensity at right angles to the incoming light, then in this case, the intensity of the light signal received by the detector will depend on the concentration of the particle and not on the size. Whereas in the case of forward scattering, The intensity of the signal received by the detector will depend both on the concentration and the size of the particle. So this is the schematic representation of the work that of the prototype of our sensor that we design in our lab. So this is the light signal. IR LED is used and from is used to illuminate the sample, which is powered from the smartphone through USB OTG cable. And this is the sample holder. It contains the water sample, and the light signal at right angles at right angle to the incoming light is received by the ALS of the sensor, ALS of the phone. So this is the representation or a prototype that we have developed in our lab. See the dimension. You can hold it on a palm of your on a palm, right? The dimension, the size of the phone is approximately 80 mm or 8 centimeter or something like that, and weight is around 60 centimeter. So it's very handy, very compact. So this picture shows where the top view of the sample holder. This is the water's medium. This is a position for IR LED, and this is the scattered signal is received by another panel, which is to the by the ALS of the smartphone. To evaluate the sensor performance, initially we prepare different turbid medium in the laboratory. This is a standard sample that we synthesize in the laboratory. There are standard chemical steps are there to synthesize different turbid medium, and we measure the turbidity level of the sample with our smartphone. So this slides represents the sensor response for different range of turbid medium that we have synthesized in the laboratory. The top panel shows the turbidity ranging from 0 to 1 at an increment of zero point 0.1 level NTU. NTU is called nephelometric turbidity unit. This is a standard unit to represent the number of particle that is present in water medium, or micron size particle that is present in water. So this is conventionally this unit is used to represent the level of turbidity. Similarly, this is another range of turbid medium from 0 to 10 with an increment of 2, 4, 2, 3, or maybe increment of 1. Similarly, another range, higher range actually, higher concentration turbid medium, 40 to 400 at an increment of 40 NTU. In all the situations, we have found that the linearity in the sensor response. This is again a very important features. As I said, that this will enable our sensor to detect the turbidity level of any unknown sample simply by putting the value in one of this graph, by plotting the putting the value, and from there I can calculate the turbidity level of the unknown sample easily. So after getting the linearity in the sensor response, we measured the sensitivity and the resolutions and what is the uncertainty, and we found that it is highly sensitive. Resolution is very good in terms of its resolution ability. It is giving you this like 6.25 10 to the power minus 4. These are little higher standard. No this I should not go this to detail the technical detail about the technicality of this. And so after having a high resolution and sensitivity, we measure the turbidity level of unknown water sample collected from different places of Tezpur and in and around of Tezpur University, and compare the data with a standard turbidity meter or a laboratory grade turbidity meter, and we found that similar data was found. There's a similarity in the data given by both the instruments. So this indicates that the proposed sensor can be used for measurement of microbial particle or measurement of concentration of microbial particle present in the water medium. Next, using the same principle, we measure the growth of pathogens or bacteria rather, which is generally required in the laboratory applications. Using the same light scattering principle, we recorded or we detected the growth of bacteria in laboratory environment. This is the setup which we have designed in the laboratory, and this is a prototype which we have fabricated on 3D printing setup. So two bacterial sample was considered for this. Were considered. One is E. coli, and this is B. subtilis. E. coli is generally present, in a rainwater during in a rainwater contamination or contaminated water. So during the growth process, usually it is seen three different phases called leg phase, log phase, and stationary phase. Similarly, for B. subtilis also the same phases were recorded, and the data were compared with a standard OD600, which I have mentioned in my earlier slide. So we found that the data as recorded by our smartphone detector or smartphone sensor and by the OD600 instrument are almost at par, or they are giving similar kind of data variations. So this indicate that my sensor can be used for monitoring of growth kinetics of different pathogens in laboratory environment. In order to establish the operation of the present sensor or the reliability of the present sensor further, we diluted the sample by 50%. So let us we consider several bacterial samples such as E. coli, S. aureus, B. cereus. These are different bacterial samples that generally researchers use in their laboratory, and we have diluted the sample by 50% every time, and we found that the sensor response is dropped immediately. The turbidity level of the sensor response drop approximately half of their present value when the concentration is changed or is dropped to 50%. This indicate that the working principle or the light scattering principle based on which our sensor was designed is working reliably on all the bacterial samples in the laboratory environment. So in the next work, what we have done, we develop a smartphone based microscope in a laboratory. So here we design a 3D printed uh, microscopic slide holder, which is this one is a microscopic slide holder that will hold a microscopic slide that may contain your blood sample or any other biological sample. And this setup is illuminated with an external LED powered from the phone, and the LED is initially collimated, and then you have a diffuser, and it is followed by an objective lens, which is basically a ball lens and a planar convex lens. This combination of these two lenses will give you a magnification of 520x, sufficient enough to image the blood cells or any other micro sized particle. And this is a 3D printed setup prototype that we have developed in the lab. And along with this hardware design, we also develop an applications, and that will enable us to obtain a better image, or you can say that a processed image once the application is implemented. So this is the image that we have captured with our blood sample captured with our smartphone, and this is a crop image shown here, and the application will process the image to obtain a better image. I'm sure that C image is better than the B, and the same blood sample was recorded by a standard laboratory microscope, and this is the same region which we have recorded with our smartphone. You can see that the results given by our smartphone and microscopic slide are almost same. So in the last part of my presentations, I would like to present here one of our very recent work is a programmable illumination multimodal imaging. So many a times actually we require our microscope to be a multimodal imaging. That means it has a feature to image in bright field mode or a dark field mode or a fluorescence mode, etc., etc. To do this, or to obtain this multimodal imaging features, we exploited a display panel, which can be your LED panels, OLED panels, or AMOLED panels, which illuminations can be controlled by the phone, which illumination pattern can be controlled from the phone itself using a program. So these are some different patterns that we have generated on the our display panels to obtain different modes of imaging. This is a complex of pattern, or you can sort of schematic pattern of the setup that we have designed on a phone. And this is because of the different pattern that we have generated on the display panel, we obtain different modes of imaging, such as one it shows the bright field, similarly dark field, and then oblique illuminations, then polarizations, and so on and so forth. So this is the prototype that we have developed using on a 3D printer. And then this is the phone, and this is the display panel of the phone, and this shows this is a multimodal imaging setup. So as mentioned, this is the display pattern for on a display pattern for bright field imaging. This is a display pattern for dark field imaging, and this is a display pattern on for fluorescence mode of imaging. And we can see for bright field imaging, this is the corresponding images of the micron size particle. This particle of dimension of 5 micrometer, which we have recorded, imaged on our smartphone multimodal imaging system. Similarly, for the same microbits, we image it under dark field modes, and this is for this pattern we can generate these dark field images, which can be clearly seen in this panel. And similarly, for fluorescence modes of imaging, the same micron sized particles or these bits can be imaged in this way. So this is the different multimodal imaging which we have generated on our smartphone microscopic system or multimodal microscopic system. As mentioned, that some biological substances or materials samples are so transparent that it cannot be seen under bright field imaging. So for instance, these human epithelial cheek cells or HECC cells, you hardly can see anything under bright field, but when you observe it under dark field imaging, you can see it clearly. But when you make your imaging system a differential phase contrast, even you can read the morphology or the texture of the cell even clearer. Similarly, this is the image which we have recorded under fluorescence mode of imaging. So out of these four modes of imaging, this dark field, differential phase contrast, or a fluorescence modes of imaging provided you or give you a better modes of imaging compared to your bright field. Similarly, this is the imaging of polarizing mode of imaging of starch sample or potato starch samples recorded with our smartphone. This is the same starch samples recorded in oblique illuminations, and this is another modes of imaging which was recorded in rainbow mode of illuminations. So these are some of the multimodal imaging that we have developed in our laboratory. So thank you for all your kind attentions. Before I conclude, I would like to thank the organizer of this event for having me here. Before I conclude my speech formally, I would like to mention once again that very recently we have incorporated one startup at Tezpur University, where the primary objective of the startup is to develop a multimodal imaging system on a smartphone, which can be used for laboratory purpose in educational institutions. In connection to this, we have received several grants from different funding agencies, and we are looking forward to take our invention into a product very soon. Thank you once again.